Hi, here I would like to talk about our project BBS plus signatures. In today's digital world, managing identity and ensuring privacy are paramount. Traditional centralized identity systems suffer from inherent vulnerabilities like single points of failure and are prone to massive data breaches, leaving users with little control over their personal information. Furthermore, standard digital signatures, while providing authenticity, often reveal more information than necessary, posing privacy risks, especially in the context of verifiable credentials. This leads to a fundamental question: how can we establish trust and verify claims in a distributed setting without a central authority, while still simultaneously preserving user privacy? The emerging paradigms of verifiable credentials offers a promising solution. VCs are digital credentials that are cryptographically secure, privacy-preserving, and machine-verifiable, empowering individuals with control over their data. At the heart of many advanced VC schemes lies the BBS Plus signature, inspired by the original BBS group signatures. BBS Plus is particularly powerful because it allows signing a vector of messages and, crucially, enables efficient zero-knowledge proofs of knowledge. This means a user can prove they possess a valid credential and selectively disclose to only the necessary attributes without revealing any other sensitive information. This makes BBS Plus ideal for applications like anonymous credentials, decentralized identity, and direct anonymous attestation. While BBS Plus offers a great privacy, a traditional single issuer setup still presents a single point of failure. If the issuer's secret key is compromised, an adversary can forge any credential. To mitigate this, we introduce a threshold cryptography. Specifically, a TN threshold schemes distribute the secret sign key among n parties, such as at least T of them must cooperate to produce a valid signature. This significantly enhances security, as an attacker now needs to compromise T servers instead of just one. It also provides fault tolerance, ensuring the system remaining operational even if some servers are offline. This approach is crucial for high-stakes applications and regulatory compliance, moving away from centralized trust to distributed trust. For our project aims to build a practical and secure BBS signature system that addresses the challenges of centralized trust and privacy. We've implemented the threshold BBS Plus scheme in Python, leveraging the BLS 12 bar 3A1 elliptic curve for its robust security and performance. Our key contributions include: first, an efficient distributed key generation process using Shamir secret sharing. Second, we focus on optimizing bilinear pairing operations, which are the most computationally intensive part of BBS Plus. Let's briefly review the core BBS Plus signature scheme. As implemented in BBS Plus.py, Python. It consists of three main algorithms. First, the key generations, and the issuer generates a secret key X and a corresponding public key X, along with a set of message generator H derived from hashing to G1. Second, the sign to sign a vector of messages. The signer chooses random nonces E and S and computes the signature component A using a specific formula involving the secret key X and the messages. The final signature is AES, and the third, verify. Anyone can verify the signature using the public key, the messages and the signature components. This is done by checking a bilinear pairing equation. If the equation holds, the signature is valid. This elegant structure is what allows for efficient zero-knowledge proofs later on. And now let's dive into how we achieve threshold signing. As implemented in threshold.py, the core idea to distribute the master secret key X using Shamir secret sharing. And the setup phase X is split into n shares, and each server receives one share to sign. Client sends the messages to T selected servers. The signing process then involves a multi-party computation. Crucially, servers engage in a commit review phase using our FCOM module. Each server generates its own random EI and SI, commits to them, exchanges commitments, and then reviews them. This ensures that the global E and S values are truly random and agreed upon. Each server then computes a partial signature components based on its secret share and its global parameters. Finally, the client collects these T partial components, reconstructs the necessary parts of the secret key using Lagrange interpolation, and computes the final BBS Plus signature. The key takeaway is that no single server ever holds the complete secret key or can forge a signature alone. Well, beyond the threshold security, our projects also implement weak, partially blind signatures. A crucial feature for enhanced privacy in verifiable credentials. The idea is that a client can get a signature on the message without revealing all parts of that message to the signing service. We achieve this by splitting the message into public info, which is reviewed, and private info, which is blinded. Before sending the message to the servers, the client applies non-linear transformations to the private info using blinding factors alpha and beta. The server then collectively signs this partially blinded message during this process. Server also contributes their own random alpha I and beta I to form global blinding factors. Once the client receives the collective signature, they use this global blinding factor to unblind it, recovering standard BBS plus signature. The beauty is that verifier only needs the public info to verify the signature, while the private information remains hidden from the issuer and potentially the verifier. This is perfect for scenarios where you need to prove something without revealing everything, like proving you are over 18 without revealing your exact birth date. So let's check our system architecture. Our setup involves a client and multiple server parties. The client implemented in client.py acts as an initiator. It sends requests to the servers, collects partial responses, and performs the final reconstruction of the signature. The servers implemented in server.py are the core of threshold scheme. Each server holds a share of the secret key and participate in the multi-party computation protocols defined in threshold.py and commitment.py. In our current demo setup, the client acts as a relay for inter-server communication. Simplifying the network layer for demonstration purpose, in a real-world deployment, server will communicate directly. All communication between the client and servers happens over TCP sockets. And for our key building blocks, our robust implementation is built upon several keys, cryptographic building blocks. First, carve.py provides foundational elliptic curve operations using the BLS 12 bar 3A1 curve, including point arithmetic, bilinear parents, and a secret hash to curve function. This is where the heavy cryptographic lifting happens. Second, commitment.py implements fcom, the function, a collision resistant commitment review protocol. This is vital for our threshold scheme, ensuring that parties commit to their random values before revealing them, preventing malicious manipulation. Third, the threshold.py also contains f0, a function for securely distributing shares that sum to 0, which is used for unbiased random parameter generation. And finally, f multi to p, also in threshold.py, provides a secure two-party multiplication protocol, essential for certain multi-party computations. These modular components work together to form a probably secure cryptographic stack. So I will have a demo for I will have a demo